In this video, we are going to look into reactions of sulfur and nitrogen compounds. First, we are going to examine sulfur-containing compounds, and those are thiols, thioethers or sulfides, and sulfonium salts. First, we are going to briefly look at nomenclature of thiols. Thiols are named by naming the longest chain that contains thiol group, that's SH group. So thiols are sulfur analogues of alcohols, sulfur-containing analogues of alcohols, and we name the longest chain first as an alkane, and then add suffix thiol. We don't drop the final E, since we don't have problem of two vowels next to each other. So naming is pretty simple, and if necessary, which means if chain contains more than 2 carbon atoms, we have to include the number of the carbon atom that is attached to thiol group. So first example is ethane thiol, no need for number since there are only 2 carbons. In the next case we have to use number, and that's 1-propane thiol because SH group is attached to carbon 1. And final example is slightly more complex, that's 3-methyl-1-butane thiol, so you can see how substituents are handled. So nothing special about this nomenclature, following usual nomenclature rule that you have learned so far. As substituent, thiol group is named mercapto. That's old name for thiols is mercaptanes. That's because they form very strong bonds to mercury. And so mercaptane actually stands for mercury capturing agent. And that name has been retained as name for functional group for substituent. So if both SH and OH group are present in a molecule, then molecule is named as an alcohol. So this molecule is 1-propanol. On carbon 3 there is SH substituent, so it's named mercapto. So this is 3-mercapto, 1-propanol. And we will now look at some reactions of sulfur-containing organic compounds. So thiols are readily deprotonated to give strong bases, thioxides, corresponding thioxides or thiolates. And so thiolate is very strong nucleophile, much stronger nucleophile than hydroxide, which means that they readily undergo SN2 substitution reactions. So with alkyl halides, they give corresponding thioethers or sulfides. Now, thioether itself is actually rather strong nucleophile and could react with another molecule of alkyl halide. The products are sulfonium salts. Unlike oxonium salts, sulfonium salts are stable salts. They could be stored there, solid white powders. They could be stored, some of them are commercially available, and they actually have some use in organic synthesis. So here is one example. Reaction of dimethyl sulfide with bromomethane results in formation of trimethyl sulfonium bromide. So stable salt. Now we are going to look at reactions of organic nitrogen compounds. And we are going to limit our study to reactions of quaternary ammonium compounds. The reason for that is that nitrogen or amino group is extremely poor leaving group. In fact, it's not even a leaving group. So when we consider hydrofluoric acid, its pKa is 3.2. So corresponding base, fluoride anion, is relatively strong base or rather strong base, and so a poor leaving group. Then we have hydroxide, corresponding acid, water, has pKa of 15.7, which means that hydroxide as a strong base is really very seldom a leaving group, very poor leaving group. And then when we look at amino group and corresponding compound, corresponding acid, ammonia, its pKa is 36. It's not even acidic. A corresponding base, amide anion, is extremely strong base, and for that reason we cannot consider amino group to be a leaving group. Of course, you may recall that we have a little trick in organic synthesis to convert poor leaving group into a good leaving group by protonation. Well, amino group is not a leaving group, but by protonation or converting it into an ammonium cation, we can make it into a poor leaving group. So this is actually the best we can do. We can make poor leaving group out of nitrogen. And you can see that by protonation of oxygen, we generate oxonium ion which has pK of minus 2.4, pretty strong acid. And so the leaving group of water is a weak base. But corresponding protonated ammonium cation has pK of 11.2. That's very weak acid, which means that corresponding base, ammonia, is still reasonably strong base and very poor leaving group. So this is really a poor leaving group. So now we have poor leaving group, and you may recall from elimination reactions of alkyl halides, fluoride as a poor leaving group only underwent elimination reactions and only E2 elimination reactions because a base was needed to force it to leave. And so in this case we have elimination as the only reaction, and it's called Hofmann elimination. So Hofmann elimination occurs on quaternary ammonium salts. So we actually don't protonate ammonium compounds because protonation reaction is reversible. And under reaction conditions, then proton would protonate hydroxide and there would be no reaction. Instead, we convert nitrogen into quaternary ammonium salt and use hydroxide ion as counter ion. Then upon heating, that hydroxide ion acts as a base, abstracts proton from beta carbon, and results in formation of corresponding alkene. The reaction is called Hofmann elimination, and tertiary amine is the leaving group. Another byproduct is molecule of water. Here is the reaction mechanism, and you can see it's concerted E2 elimination. So hydroxide as a base picks up beta proton, and that forces electron pair that proton used to share with carbon to move, to flow, to form carbon-carbon pi bond, and that will result in simultaneous breaking of carbon-nitrogen bonds. Reaction is regioselective, and as you can expect, regioselectivity is Hofmann regioselectivity. That's why regioselectivity in fact is called Hofmann regioselectivity. This is 19th century reaction. It was discovered by August Hofmann, German chemist, and it was observed that it occurred with unusual regioselectivity where less stable alkene, less substitute, less stable alkene was formed. If there are two different substituents on nitrogen, and since nitrogen has 4 alkyl substituents, it could have 2 different substituents with 2 carbons of more that could eliminate. If there are 2 different substituents, then substituent that forms less substituted double bond is one that will undergo elimination. So here we have 2 substituents on nitrogen, elimination of substituent on the left, 2-methylpentyl substituent would result in formation of di-substitute double bond, while elimination from propyl substituent results in formation of 1-propene mono-substitute double bond. So 1-propene is the reaction product, Hofmann reaction product. We can explain regioselectivity of Hofmann elimination by considering transition state. And in fact, we looked at it already, if you recall, in chapter 14. So reasoning is the same. In this case, we have elimination from 2-pentyl substituent. And so products could be 1 or 2 pentenes. Major product is 1 pentene. So now we have trimethyl ammonium substituent that is the leaving group. It's a poor leaving group. And so as hydroxide, in the transition state, as hydroxide donates electron pair to beta hydrogen, it forms partial bond to hydrogen. That results in partially broken carbon-hydrogen bond, and then down the chain, partially formed carbon-carbon pi bond and partially broken carbon-nitrogen bond. But because nitrogen is a poor leaving group, it's not leaving a negative charge backs up on that middle carbon in the middle of the chain. As negative charge backs up, that carbon resembles carbanion, and stability of that carbon and then correspondingly transition state corresponds to stability of carbanions. Again, you may recall from previous analysis that less substitute carbanion is more stable one, because more substitute carbanion has electron donating substituents, and they are donating even more electron density on already negative electron-rich carbon that is unstable, and they are destabilizing it further. So the fewer the substituent on such carbon, the better. So for that reason, transition state that leads to formation of less substituted alkene is one that has less substituted carbon. And that's lower energy transition state, so that reaction proceeds faster, and of course reaction is kinetically controlled. Alternative transition state is higher energy because negatively charged carbon, partially negatively charged carbon is more substituted. Again, if you recall, the same analysis applied to fluorine as the leaving group, and we covered that already in chapter 14. Of course, if we want to carry out elimination on quaternary ammonium hydroxide, first we have to prepare it. And here is an example of preparation of such compound. We start with amino compound, and then we carry exhaustive methylation with iodomethane. We can examine that on example of 1-butane amine. So we treat 1-butane amine with excess of iodomethane in the presence of potassium carbonate. Potassium carbonate is used as mild base, and it reacts with any evolved hydrogen iodide to keep reaction mixture or reaction solution neutral. So product is butyl trimethyl ammonium iodide. Of course, this is not hydroxide, and now we need to replace iodide anion with hydroxide anion. To accomplish that, we need to add hydroxide, some hydroxide that will react with, whose cation will react with iodide anion to form a precipitate, and that way take it out of the equilibrium. That way only ammonium hydroxide would be left in solution, and then upon filtration we'll have solution of ammonium hydroxide, and if necessary we can of course evaporate it if you want to isolate it. A cation that forms precipitate with iodide anion is silver. So we need to use silver hydroxide. Problem is that silver 1 hydroxide doesn't exist. It's unstable. If you attempt to prepare it, silver 1 oxide is going to precipitate. But what we do is we use a wet silver oxide. That's a mixture of silver oxide and water. Wet silver oxide actually reacts as silver hydroxide, and so we use that slurry, stir it, and a reaction occurs as if we were using hypothetical silver hydroxide, and reaction will proceed in such a way that quaternary ammonium iodide will produce quaternary ammonium hydroxide, and silver iodide is going to precipitate. And so upon filtration we end up with solution of quaternary ammonium hydroxide, and then upon heating, quaternary ammonium hydroxide is going to undergo elimination to give product of Hoffman elimination product. In this case, product would be 1-butane. An alternative method to carry out elimination of amino compounds is Cope elimination. This is more modern method, and experimentally it is easier to carry out. Cope elimination is carried out on N-amine oxides. And in this case, as you can see from this equation, base, oxygen, is part of the molecule. So reaction is unimolecular reaction. So we prepare N-amino oxide, and upon heating in intramolecular reaction, elimination occurs. Reaction is still Hoffman elimination. So regioselectivity is still Hoffman regioselectivity. N-amino oxides are prepared by oxidation of tertiary amines with hydrogen peroxide. So as you can see, reaction is much easier to carry out. Simply we prepare tertiary amine if necessary, unless you already have tertiary amine. So through methylation we prepare tertiary amine, oxidize it with hydrogen peroxide, and then upon heating elimination occurs to give Hoffman elimination product. This completes our study of sulfur and nitrogen containing organic compounds, and next we are going to look into spectroscopy.